Okay, let's go from current slide. All right, we're back in business, and we got lights, cameras, action, everything. Okay, chapter 14, if you remember, started with the universe, okay? Then we narrowed down to the solar system, basically. And now in chapter 16, we're talking about the Earth in space. Now, I actually count this as the Earth-Moon system in space, though we'll talk about bigger things as well. The core concept here, found on page 407, is the way the Earth moves in space is used to define time and describe location on the surface, and causes other recurrent phenomena such as the seasons. We get time of day, we get time of year, we get seasons, we get other issues like this. Another pretty picture here, not very realistic, but I guess a pretty picture. I assume this is taken from the moon, okay, or the other side of the moon, where you're much closer to the moon, and that, I guess, would be Mercury, Venus, though the perspective is off. That's probably Mars. This is Earth. One of those is probably Jupiter and Saturn. Obviously not to scale, just some artist's rendition, okay? Now, let's start with the shape and size of the Earth. This is section 16.1. The Earth is not a perfect sphere. It's what they call very close to an oblate spheroid. What? Okay, spheroid meaning it's like a sphere, but it's not quite. Here are deviations. It's slightly pear-shaped, a little bit thicker. Don't want to do it. Okay, a little bit thicker at the bottom part, not quite as thick in the upper part. Now, this makes no sense to me at all. I guess somehow it does to somebody. It says there's a lump in the Pacific. Now, wait a minute. The Pacific is water. How can you have a lump in water? Okay, except that maybe the water is pulled outward somehow. I don't know. It doesn't make sense. And a depression in the Indian Ocean. Well, wait a minute. If it's a depression in the Indian Ocean, wouldn't water be running into the depression and it would all even out? I don't know. I cannot describe this for you. It's not explained well enough in the book for me to tell you what they're talking about. But the elevations and depressions in deviations is less than 85 meters. Now, what's 85 meters? Less than a football field. Football field from, say, end zone to the opposite goal line is pretty close to 100 meters. So 85 meters is pretty small compared to the size of the Earth. So don't sweat lumps in the Pacific and depressions in the Indian Ocean. That kind of doesn't make sense. But what it means is the overall shape is that. Okay? Now, don't think this is where it's broken away from being a sphere. That's just because this is in the shadow. That's not. But, you know, this part here, that looks awfully circular to me. Okay? But there are problems, and here's what it means. The actual sphere would be the dotted circle here. That is an actual sphere. What we are, the Earth, is a little bit fatter around the equator and a little bit narrower in the at the polar regions. Okay. Now, what I can't quite figure here, if you look at kilometers here, 12,714 kilometers this way, shorter than this way, 12,756 kilometers that way. If you take the difference between these two, you get 42 kilometers. That's not 85 meters, okay? So I don't know if the elevation depressions there are talking about the changes here. I think this is just talking about the pear-shapedness of the Earth. Still not much change here. This is just 42 kilometers. That's about the distance from here to Birmingham, maybe. So that's in the whole Earth. That's the only difference. It's not very much. Not very much at all. Okay. These, I think, are your depressions and the deviations there. That's even less. Way, way less. Okay. Now, to me, these are a little more interesting. These are the motions of the Earth. But before we get to that, remember the figures I mentioned before, that the distances were such out of proportion, but the relative sizes were close. These are even better relative sizes. Now, this isn't in your slide set, but I found this pretty interesting. If we put, I guess this is Mercury here, which looks bigger than Mars, but it's not. We know that, but it's just because it's closer. Venus looks bigger than Earth, but it's not because it's a little closer. Then Mars, this would be the size of Jupiter, relatively speaking. There's the great red spot. It looks like you could fit all four of the terrestrial planets in the great red spot with plenty of room to spare. That just shows how enormously large Jupiter is compared to the four terrestrial planets. Saturn, not far behind, but still much smaller than Jupiter, and it's much bigger than Uranus and Neptune. So those are just, that's probably your size relations far closer than anything else we saw earlier. Distances, of course, are not even, they're not even pretending those to be the case. Just to give you an idea too, remember the ecliptic we talked about when we were doing the first lab? This is a picture of the, pretty much of the ecliptic, and notice how all the planets are pretty close to that because they are in that same disk around the sun. There's Saturn, Mars, Jupiter, Mercury, you'll hardly ever see, but it's right in the, very close to the pattern of the sun. Okay? This just shows that one particular night, you can see that many. They put in the ecliptic. You are not one particular night. One particular superposition of the position of the sun over time. You know, sort of hard to do, but they list several of the other big stars like Antares. We mentioned that before. Spica, I don't remember if we mentioned Spica before. Spica, and Regulus, awfully close to the ecliptic. Okay. Just since I had it up there. Now let's look at motions. This is 16.2. Relative motions of the Earth. 3 of these Earth motions are completely independent of the motions of the sun and the galaxy. They have nothing to do with the movement of the sun or the movement over the galaxy. Okay? This is just the motion of the Earth. Our yearly revolution around the sun, if Amanda was the sun there, we go all the way around in the course of a year. Our rotation about the axis, this is a revolution, that's a rotation. We do that once every 24 hours, we spend one time around. 365 days and a fraction to go around the sun. Now, these two, 365 days, 24 hours, I don't even know why they put this one in here. We have a clockwise wobble in our rotation axis. That happens on the order of something like 25,000 years. So, completely different ballpark time-wise from what these are. These are years, days, 27,000 years. Okay, nowhere close. But we do that, and that's completely independent of the sun or galactic motion. Okay, now let's get the specific motions. Okay, 7 conspicuous motions of the Earth through space. Well, this is going back to our rotation. At the equator, which is the place further south, so it's going to be going the fastest, that daily rotation, if you were standing on the equator, Quito, Ecuador, somewhere like that, and you would be traveling, not realizing you're traveling, 1,600, well, let's see, that's kilometers per hour, 1,670 kilometers per hour, which multiply that by 0.6, about 900 miles per hour, approximately, at the equator. That's how fast you'd be moving. You wouldn't notice it. You'd be going about 900 miles per hour. Okay? Now, your monthly rotation about the Earth-Moon center of mass. We'll talk about this later in the chapter. But because our moon is so big compared to our Earth, our planet Earth, no other Earth-Moon planet-moon system in the solar system is anywhere close to being as close in size as ours are. We're much bigger than the moon, but the other moons compared to their planets, minuscule. Grains of sand, okay? Not us. Because of that, when the Earth moves, the moon moves around us, we move a little bit too. Not much, but a little bit. That's what they're talking about, the monthly rotation about our Earth-Moon center of mass. We're so much more massive than the moon, but you'll see an illustration of this later in the book, but the center of mass of the Earth-Moon system would be something about like here. Not on our axis, which if we had one of those little moons, it would be almost right on the axis. Somewhere here. Still within the Earth, so we do this while the moon does that. You know, so it's not a big thing, but just a little thing. Okay? A yearly rotation about the sun, in that respect, we're going about 106,000 kilometers per hour, which would be about 60,000 miles per hour. Moving along pretty rapidly there too, folks. Okay? The orbit of the solar system about the center of the Milky Way. Remember, the Milky Way has that blob in the middle, okay, the galactic cluster in the, well, that's not what it's called, galactic mass of stars there that's in the center. We're on one of the spirals about 2/3 of the way out, so we're spinning around that center of the galaxy. That's what this one is, the orbit of our solar system about the center of the Milky Way, and we're moving about 370,000 kilometers per hour, which would be about 200,000 miles per hour around that way. The orbital motion within the stars, the sun's local star group. So we have a little group of stars around our sun, not around our sun, we're in the star group. Maybe a small black hole we're moving about. And that's about 1 million kilometers per hour there within the local star group. And that would be about 600,000 miles an hour. We are moving. We don't realize that we are. Now, the motion of the Milky Way galaxy relative to remote galaxies, that's about 580,000 kilometers per hour, which would be about 300,000 miles, 350,000 miles, something like that, an hour. Now, minor motions. These are pretty fast, most of those. The changes in the shape and size of the Earth's orbit. Okay, that's our orbit around the sun. We deviate slightly there. Okay, sometimes we're closer to the sun. At what month of the year would you guess we're closer to the sun? Say again? Did someone say something? June? okay, July, something like that. No, we're closer to the sun in January. We're farther from the sun in July. That's our furthest point. Now, that has nothing really to do with the seasons. That's all dealing with the tilt of the Earth, okay? But that, if anything, would moderate our seasonal differences. That means the southern hemisphere, Australia, is actually closer to the sun in its summer and farthest from the sun in its winter. So you would think it probably had greater temperature differences between the two. I don't know if that's measured, if they actually determine that or not, and here's why. What do you notice about the northern hemisphere as compared to the southern hemisphere? Southern hemisphere, northern hemisphere. A lot more land in the northern hemisphere. Land has more differentiation between temperatures because it gets hotter in the summer and cooler in the winter. Water is a big equalizer. So that may keep the southern hemisphere from noticing the differences that you might suspect from that. So that's changes in the shape and size of the Earth's orbit around the sun. Changes in the tilt of the Earth's axis, that's the one that's incredibly slow. Okay, incredibly slow. Okay, it's the one we mentioned before on the other slide. Now, here's another one. We seem to be slowing ever so slightly in our rotation rate. It may be that in the past at one time we were only 23 hours and some odd minutes to make one spin, and now we may be slowing a bit, so it's taking a little bit longer. But the odds are we're changing our hour to fit that. I don't know how we're dealing with that. It's a these are minor motions differences, not anything compared to the speed you see here. Okay. Now, the overall picture from space, okay, is that we're moving along a helix. Anyone know what a helix is? It's a spiral type thing, okay? Moving along a helix at incredibly fast speeds, okay? Because here we are in our solar system moving around the Earth, around the sun, okay, and that's what we think we're doing. But you see, the sun is moving this way at really high rates of speed going around the center of the Milky Way. So that makes us doing this kind of motion as we go. Now, it doesn't look like they got these quite far enough out here, but yeah, that's what we're moving around like that. That's the helix. Excuse me, they're talking about. Now, viewed from the Earth, the ecliptic plane is the plane of the Earth's orbit around the sun. So again, if Amanda was the sun there, this plane that we make as we go around the sun, that would be the ecliptic for us. Okay. The planets move in a narrow band around the ecliptic, and that's what I showed you in the just a little bit earlier. That picture on page 409. They're not quite on the ecliptic, but close, and that's because, you know, they all have slightly different tilts to their axes. Not far, usually less than around a degree or so. So that's why they're not quite on the ecliptic. So we don't fit exactly in one flat disk. We have a little bit of variation between the planets. Okay? Move in a narrow band about the ecliptic. Solar system is relatively flat. At least the planet part of it is. Okay. The Oort cloud is three-dimensional. The Kuiper belt is pretty much three-dimensional. Well, it's thicker. The sun moves along the ecliptic across the background stars. Now, that's what it appears to be. Actually, what we do, we move here. So when we're here, the sun seems to be in the midst of these stars. When we get over here, the sun seems to be in the midst of those stars. So it's not that the stars are moving or the sun's moving, it's we're moving around the sun, putting the sun in the background of different stars in the background at different times of year. Okay. I think we beat that to death, didn't we? All right. Now, that was our overall. Let's take the individual ones. Starting with revolution. No, not that kind. Okay. The Earth's movement around the sun. The orbit defines the plane of the ecliptic. Okay. How many times are we going to say that? Enough to mispronounce it more. The ecliptic is the apparent path of the sun through the heavens as seen from the Earth. Okay? So, for instance, right here, I'd be looking at stars behind you. Sometime later, I'm looking at a different group of stars. Okay? Different times of year, you'll see different ones. And that's why you see different constellations at different times of year, because you're looking at different groups of stars. Okay? The elliptical orbit, okay, not circular. So don't get confused. Ecliptic, that's where the sun is eclipsing something behind it. And elliptic, which is an elongated circle, ever so slightly. And we're about 2.5 million kilometers closer in January than we are in July. 2.5 million kilometers more distance in July. Now, I don't know if that's total difference or if those add to be 5 million, but what's 5 million among 193 million miles? So how many miles would this be? 6 times that. Goodness, my math is slow today. About 1.7 million miles, okay, something like that, as opposed to 193 million miles. Not much difference, less than 1/10 of a percent. The Earth receives about 6% more solar energy in January than it does in July, but we don't notice that because in January we're pointed away from the sun, in July we're pointed toward the sun. Even though we're further away, we get more. But the southern hemisphere, that's the one that would be magnified. If it weren't for the fact that there's so much water down there around it. Okay. Make sense? Move on. Okay. Now this is an exaggeration, and it does it for a reason. But it's not this distinct. We're not that much further than we are here. This is December. We're actually closer. June, we're actually a little further away. We're not at the farthest part, but we're pretty close to it. What makes our difference here is that tilt of the Earth. What is that tilt? Anyone remember how many degrees? 23.5. Perfect. 23.5. Okay? Now that means that the ecliptic of the sun intersects on March the 21st and September 22nd, or somewhere around that. You know, we've been saying March 21st as if it's always fixed, but it varies a little bit year to year. September 21st, 22nd, 23rd, sometime in there. The sun's ecliptic is right on our equator. It's directly overhead on those dates. And what are those dates called? The equinoxes. The vernal equinox, which means spring. The autumnal equinox, which means fall. Okay? The sun is directly overhead. What is this date? December the 22nd, 23rd, 21st, sometime in there.
Winter solstice.
The what?
Winter solstice.
Winter solstice. That's as low as the sun was ever going to go. It's going to be directly overhead. What line down here? What circle down here? Tropic of Capricorn in the southern hemisphere. And in the northern hemisphere in the summertime, the sun is going to be directly overhead in the Tropic of Cancer. Exactly. So in between those two dotted lines, that's what we call the tropics. You see those two dotted lines go close to northern Cuba. So southern Florida is not quite in the tropics, but it's awfully close. It's semi-tropical. Okay? All of Cuba is in the Hawaii is our only state in the U.S. that is in the tropics. A few of the northern islands are close, but they're still in there. And it goes on around. Okay. That's the tropics. Okay. Tropic of Capricorn down here where the sun is directly overhead on the winter solstice. Tropic of Cancer, which is 23.5 degrees north. And by the way, that's our 23.5 degrees again, showing up over and over. And that's the Tropic of Cancer in the northern hemisphere. It's where the sun is directly overhead on the summer solstice. Okay. And so, yeah, this is where they give the names down here of what they were describing here. Now, again, this is not nearly as off-center as what they're picturing. It's just slightly closer here than it is here. They've exaggerated this big time. All right. That's our revolution. Now, what does that mean? In between the autumnal equinox, which is coming up in about a month, or less than a month, to the winter solstice, this is our fall. Between winter solstice and spring equinox, that's our spring. That's our winter. Between spring equinox and summer solstice, that's our spring. And between summer solstice and autumn, that's where we are right now. We're still in summer, in the last 2/3 of summer. There's our seasons. So that's one way we keep track of time. Spinning, that's our hour, that's our day, and revolution, all the way around, is our year. Okay, so let's get to our spinning, our rotation and the Earth's axis. The Earth's rotation axis is inclined 23.5 degrees. Okay, as shown. I guess they need me to show it again. There we go. Okay. The seasons are determined by the orientation of the rotation axis. Okay. So between spring equinox here and summer solstice there, that's our spring season. Between summer solstice and autumnal equinox, that's our summer season. And we're right about there right now. Between autumnal equinox and winter solstice, that's our fall season. Between winter solstice and spring equinox, that's our winter season. Okay. I was tracing the ecliptic. I should have been tracing the Earth, and this is us here. We're up here. We're along that. All right. Not that it matters. All right. The seasons are determined by the orientation of the rotation axis. Winter solstice, summer solstice, that's as low in the sky or high in the sky in the northern hemisphere as the sun ever gets. Solstice meaning sun, sol, cease, still. The sun quits rising. Had been up to then every day leading to the summer solstice. The sun was getting a little higher every day when it crossed our meridian until it reached the peak, stood still, and after that starts going down a little bit every day. Goes down every day until it reaches the winter solstice. Sun stands still again, stops going down, starts going back up again. Okay, that's why the big parties were in winter solstice when the sun stopped going down and promised to come back and not fall below the horizon and everybody died. Okay, spring equinox, equal night, equal day, equal nox, night, equal night and day. Autumn and spring. Celestial equator, this is the celestial equator, the pink one. They don't label it there, do they? I don't see it. But anyway, that's our tilt. Here is the actual equator around there. There's the projection of that out in the celestial sphere for the celestial equator. The line on the celestial sphere above the Earth's equator. Not a great picture, but pretty close. Just looks like to me the North Star is not quite in the right place, but that's my perspective. All right, any questions on that? All right. Now the question, how do we know the Earth rotates? Does it really rotate? Could those stars really be going around us? We don't think so, but here's 3 observations that you get. And Galileo was one of the first ones to do this. He realized that Jupiter was rotating, that great red spot up until it was rotating, it's spinning. The sun, because of the sunspot. Now, don't ever look directly on the sun, but look at a reflection or something like that. Pictures of the sun, things like this, and you can see the sun is rotating too. If they're rotating, why wouldn't we? Okay, that's one. Another, does anyone know what a Foucault pendulum is? I don't know if I'm pronouncing that right. Foucault, I don't know how you pronounce it. It's a French word, so it's pretty strange. Has anyone ever been to the McLean Science Center? Okay, do they still have that big pendulum over in one corner that goes back and forth? It may not. Okay, I didn't remember saying the last time I went, but for a while they had one. That's like a Foucault pendulum. There's one in France, I think somewhere in Paris, where probably he did his first one. If you watch that pendulum go, okay, and if you have outlined on the floor there, which they used to have in the McLean Science Center, the times and days and things like this, and if you watch that pendulum makes this kind of a pattern. It actually doesn't change much each time it goes back and forth, but it changes just enough that in a day it's going to hit. If you marked out even spaced hours, it would be at the hour every time. The pendulum is oscillating in a fixed direction, but orientation changes as the Earth rotates. It does. You can do that. It's sort of like, let's see if they have this figure here. If you had a stool which spun, okay, and you had a pendulum here that was just going back and forth. This isn't 2 balls. This is 1 ball hanging down, going back and forth. Spin the thing. Sometimes it's going like this, sometimes like this, sometimes like this. It's changing as it goes around. If you were on the plate, it looks like it's the same. If you were spinning with the top of the stool, it looks like it's always the same, but it really isn't. It's actually changing direction as it goes. Okay, so the Foucault pendulum will oscillate and changes, orientation changes ever so slightly every movement back and forth. The third one of these is the Coriolis effect. By the way, there's a name, Foucault. Who in the world was he? How did he do this? Could be a paper topic, couldn't it? Coriolis, there's another name. Good Irish name. No, I mean Italian name, right? Okay. Deflection of paths as the Earth rotates beneath moving objects. It's sort of a weird way to say it, but if anyone was actually a fire control technician, you have to adjust for this ever so slightly, but you do have to adjust because you fire something into the air, it's going to do like this because the Earth is spinning under. It really isn't twisting, it's the Earth doing, and you had to account for that, didn't you? Yeah. So, Coriolis effect. Here's another. This is one that you have probably noticed but never realized. Okay. Do y'all like to look at weather maps? High pressure areas, low pressure areas? Know anything about that? High pressure areas, the winds always circulate clockwise. In the northern hemisphere, low pressure area, they circulate counterclockwise. And that's because winds flowing this way, because of the Earth's spin, it deviates. And when the wind's moving up, it deviates in the opposite direction. Now, here's some place you probably all have seen it, and probably never wondered about it, but hopefully from now on you will notice it. When you pull the plug on the sink, on the tub, or flush the toilet, okay, what do you notice? It spins. It doesn't just, does it? It actually spins. Okay? The reason for that, the rotation of the Earth. If the Earth wasn't rotating, it would just go down. But because it's rotating, it gives that spinning action. Now, if you were right on the equator, it probably pretty much goes straight down. I don't know. But in the northern hemisphere, see, that's a low pressure area. It spins counterclockwise. Now, this just is an illustration of how weird a physicist can be. And it's just a minor illustration. But when I was an undergraduate, I had a professor for at least, I can think of 2 classes, maybe 3. Dr. Young. He was a big honcho in crystallography. Okay, he was editor of one of the major international journals on crystallography. And he got to go when he was editor, they happened to have their annual meetings in Rio de Janeiro. Right there. It's on the coast of Brazil. Okay? Now, anyone know anything about Rio? It's the party city of the Southern Hemisphere. Or at least that's its reputation. It is a fun place out here. I've never been there. Okay? But supposedly it was. Well, their annual meeting or their semi-annual or however, biannual, whatever meeting of the International Crystallography Association Society, whatever, was meeting this time in Rio. And he was so excited to be there. When he got off the plane and into this hotel room, he put down his bag, rushed into the bathroom to flush the toilet to see the spin go in the opposite direction. That's a physicist for you. His excitement was to watch the Coriolis effect rather than being in Rio, the party city of the Southern Hemisphere. Okay, so dumb story. Okay, Coriolis effect. It wouldn't happen if the Earth were spinning. Okay. Any questions? All right. How are we doing? Huh?
It's 5:10.
5:10. Okay. It looks like we probably beat that one to death. Let's start next time with precession. That seems like a good place to pause here. We'll start with precession on the next go around. Okay? So, I know we've had a few breaks, but this was a bad one. That if anyone wants, so we had a few more quick notations of things on your formula and equation sheet. You certainly can do that. If you want to just get up and stretch, get blood flowing, that would be a fine thing to do. I'm going to be taking this down, so if you want a restroom break, bladder break, something to drink, something to eat,